Control Systems, Chapter 4, Lecture 1, Time Response. So in Chapter 2, we saw how transfer functions can represent linear time invariant systems. Once we've determined a mathematical model of a system, the next step is to analyze how the system responds to various inputs over time. This can include both the transient response and the steady state response. Together, these responses reveal whether the system performs as intended. So the goals for this lecture are to understand the relationship between the system structure and time response. We're going to examine how input types affect the system behavior and learn the role of poles and zeros in shaping the response. We're also going to explore practical ways to determine transfer functions from experimental data. And that'll be determined in future lectures in this chapter. In this lecture, we're simply going to look at the general structure of how this works. So after we obtain a mathematical representation of the system is analyzed for its transient and steady state responses to see if these characteristics yield the desired behavior we need. Typically, we want to test our model by applying an input signal and observing the output response. So the process model, that's our system. That's our model that we've come up to model a particular situation we're dealing with. So how do we test this? Well, we input a known function, either a step function or a pulse or sinusoidal wave that gets processed through the model, and then the output is what we measure. And if our output is what we expect, then we have our model is good. So let's imagine we're modeling a bucket of water being filled with water. So what would the input be? Well, the input here is simply water that flows into a bucket, and we can let this flow happen in various ways. That's our input. The output we're going to measure is the height of the water in the bucket over time. So this process model, this would be the mathematical model of how this bucket would fill over time. It's basically how the output relates to the input. So what are some common input signals? Well, first we have a step function, which is simply like a sudden change, like flipping a switch on. There's a ramp, so you have a gradual linear increase over time. A parabolic input signal. You can have an impulse, a rectangular signal, or you can have a sinusoidal, continuous periodic input signal. So let's take a look at what these look like on a time versus input graph. And so a step function simply is 0 before you turn it on, and then it's 1 afterwards. So here, if you took the Laplace transform of this input, this is the step function. It's simply a over s, where a is the magnitude. It's a constant. And again, we're transferring from time space to s space. A ramp simply looks like this. It's a y equals mx kind of straight function. It's got a constant slope. So here our function is represented by this mathematical model in time space. At t less than 0, it's 0, and t equals 0, it has a constant slope. If you take a Laplace transform of this function, you get a over s squared. Similarly, a periodic input signal is simply a square function, right? A is a constant. Laplace transform is a over s cubed. For a rectangular input signal, it's simply a pulse. The Laplace transform is h over s times the quantity 1 minus e to the minus t times s. Impulse simply is 0 before it, and it turns on and off, right? So it's a impulse function, a Dirac delta kind of function. And the Laplace transform here is this 1. The sinusoidal input function, the Laplace transform a omega over s squared plus omega squared, plus or minus omega squared. So in general, the total response of a system is the sum of two parts. It's the sum of the natural response and the forced response. The natural response depends only on the system and not on the input. So, back if you remember back when you were taking differential equations, or maybe you're taking it now, but when you end up solving uh, you know, uh, a non-homogeneous differential equation, uh, you have a homogeneous solution and you have a particular solution. The natural response is the homogeneous solution, where you set the right-hand side equal to 0. The particular solution is that's the forced response, and it's dependent. That's what's depending on the input. So in general, you have the total response is the sum of these two parts. So instead of solving differential equations, though, which can be kind of laborious, we're going to use Laplace transforms. So Laplace transforms allow you to solve these kind of differential equations using algebra instead of differential equations. So the key insight into a system's behavior can be obtained by expecting two things. So once you take the Laplace transform of your differential equation, you look at what's called poles, which are roots of the denominator, or you look at zeros, which are roots of the numerator. And we'll see some examples of how this works. So what are the poles? The poles of a transfer function are defined to be the values that make either of the following conditions true. They're the values that cause the transfer function to become infinite. So that would be something in the denominator. So 1 over s squared, well, if s is 0, then 0 would be a pole because that makes the transfer function become infinite. It's also any roots of the denominator that are common to roots of the numerator. Those are also defined as poles. Zeros are defined to be values that make either of the following conditions true. The values that cause the transfer function to become 0. Or there are any roots of the numerator that are common to roots of the denominator. Those are also zeros. So let's take a look at a very simple system. So here's our transfer function. G sub s equals s plus 2 over s plus 5. So first we look at this, it has a pole at minus 5, because if you plug in s equals minus 5, that makes the g sub s go to infinity. And it has a 0 at s equals minus 2, because if you plug in s equals minus 2, that makes g sub s 0. So typically what we do on these is we plot these on a pole 0 plot in the s-plane, where we have real values on the x-axis and imaginary values on the y-axis. That's indicated by the j omega. So here we plot, since s equals minus 5 is a pole, we plot that using an x at minus 5. And since s equals minus 2 is a 0, we plot that as a circle. So this is one way to plot, this is called a pole 0 plot, because you can plot, this is how you plot them. Let's take a look at this function. So here, you can find the properties of this function. Let's imagine here's our transfer function, and we're going to input a step function, 1 over s. So what comes out on the other side, c sub s is equal to g sub s times r sub s. So that would be 1 over s times s plus 2 over s plus 5. So here, this is an S space, so we can use the partial fractions to break this apart. We just have to determine what A and B are. So if you use algebra to determine what A and B are, you get A is 2/5 and B is 3/5. So here, if you take this function now c sub s and you do an inverse Laplace transform, what do you get? Well, you get 2/5 plus 3/5 times e to the minus 5t. So what do we learn from this? We're trying to learn how to determine the information from Laplace transforms without having to find the time-based function. So here we can plot this. We know what this looks like. So let's take a moment to notice the following relationship between the c sub t and the time base, the time domain, and also how that relates to the transfer function g sub s. So here's c sub s. You know, we found that it was a was 2/5 and b was 3/5, and we did an inverse transform of c sub s to find the c in the time domain. But notice here, if you let s go to 0 in g sub s, what do you get? Well, you get 2/5, which is exactly the value here for a. And if you let the s go to -5, uh, what do you get? Well, you get s plus 2 over s, which turns out to be 3/5, which is exactly the b value. So what are some lessons we learned from this example? Well, first, a pole on the input function generates the form of the force response. So that, in other words, the pole at on the input function, which is 1 over s, that's the 0, generated the force response. You got the 1 over s value. Secondly, a pole of the transfer function generates the form of the natural response. So in other words, the pole at -5 generated e to the minus 5t. So here was a pole on the s plane of the transfer function that generated e to the minus 5t. Third, a pole on the real axis generates an exponential response to the form e to the minus alpha t, where minus alpha is the pole location on the real axis. So for here example, here's a pole at -5 that generated the e to the minus 5t. We also note that the farther to the left the pole is, the faster it would decay to 0. So if this was -7, it would have been e to the minus 7t. And finally, the zeros and poles generate the amplitude for both the force and natural responses. So here, for example, the -2 and the -5 generated the 2/5 and the 3/5. Okay, so the next lecture we'll look at first order systems.